In this tutorial, I will show some specific features of the Chymyst library implementing the chemical machine in Scala, namely the ability to construct reaction sites at runtime from a number of reactions that are parameterized by runtime parameters. I will use two examples to illustrate these features. The first example is the dining philosophers problem. I already explained this problem in a previous tutorial, so here I will only show how to solve this problem for a variable number of philosophers that is only known at runtime. The second example will be Conway's game of life. I will be able to show a fully concurrent solution for the game of life where the cell updates are completely parallelized both in space and in time. To begin with the philosophers, the simple solution we have seen before is for a fixed number of philosophers. So for 5 philosophers, for instance, we have to introduce 5 molecules H1 to H5 representing hungry philosophers. Also 5 molecules T1 to T5 representing thinking philosophers, and the 5 fork molecules representing the forks between each pair of philosophers sitting next to each other. Now the code that simulates the dining philosophers for a fixed number of philosophers is very simple. Conceptually, it's very simple. It is declarative. If the philosopher is thinking, then it waits and becomes hungry. If the philosopher is hungry and 2 forks are available, it starts eating, and after that becomes a thinking philosopher and the forks are again available. So this is a completely declarative solution, but it has a drawback that the number of philosophers must be fixed in advance. It cannot be made a parameter. So the reaction site, needs to be declared at some point, and once it is declared, the number of reactions in it and the kinds of reactions are fixed, they're immutable. So we cannot use this to implement the dining philosophers problem, where the number of philosophers is given as a runtime parameter. To the right of H1 is fork 1, 2. To the left is fork 5, 1. How do we solve this problem? The way to solve this problem in the Chymyst library is to declare molecule emitters and reactions separately and to assemble a reaction site from them, rather than to declare all reactions together in line in the reaction site declaration. So what we will do is we will just create data structures containing molecule emitters and reactions. Since both molecule emitters and reactions are values in the sense of Scala, we can just have a sequence of molecule emitters or a sequence of reactions. So here's how we can do that. So let's have a function, run philosophers, that will take the number of philosophers as a parameter. And it will do what the previous test did with no changes, except that the number of philosophers will be variable. So for convenience, let's number philosophers from 0 to n-1. We first declare a sequence of molecule emitters representing thinking philosophers. So to do that, we do a map on the indices And inside the map, we cannot really use the macro M very well. We could use it, but then the molecule name would not be dependent on I. We would like molecule names such as T0, T1, T2. But the M macro would not be able to do that. It's okay to have molecules with the same name. They will still be different molecules. The name of the molecule is only a debugging aid. It has no effect on the actual execution of a chemical program. But it's just inconvenient to have reactions that you cannot debug and visualize very easily. Very little work. We just use the constructor of the M class and specify the name of the molecule like this. So then we construct an array of molecule emitters for the hungry molecules, and we construct an array of forks. So the fork will have a name like this. Here we had names fork 1, 2, but since we're having an array, this could be a larger number, say 20 different philosophers or so. So let's separate the name, the numbers of philosopher to the left, philosopher to the right by a colon, and have a name like this. So we are just using some simple math to create a sequence of new molecule emitters with these names. This is purely for convenience. Now, the sequence of forks to the right of a given philosopher would be just computed with this index substitution like this. So, for example, fs left of 0 is this fork, and fs right of 0 is this fork. So then it will be easier for us to create reactions. So at this point, we have only created molecule emitters. So these molecule emitters don't yet do anything, and they're just different molecule emitters with different names. So we need to create reactions for them. So what are the reactions we want? Well, for each of the thinking molecules, you want a reaction like this. So let's do that. Here's how we can do that. So, for example, we want to create an array of reactions for thinking molecules. Each reaction would look like this. So we again do a map on the indices. Now indices are just a range from 0 until n, just so that we don't have to repeat all the time. But now notice we want to define a reaction that depends on a parameter I. So that's not a problem. A reaction is a value. So we just create a reaction like this, and it depends on the parameter I. However, there's a syntax limitation in Scala in that the left-hand side of a case expression cannot be an expression that you first evaluate and then use as an unapply object. So we would not be able to write like this. This is an incorrect syntax in Scala. So the way to go around this limitation is to define a name, such as T, for this emitter, and then we just use this T on the left-hand side of the case expression. Now, on the right-hand side, there's no need to do that. We could just do this. So let me simplify the code and do that. But on the left-hand side, I must have a new name, T, which is just for syntax purposes. Let's create reactions for eating philosophers. So for instance, a reaction like this. And we want to create a reaction like this for every index I. So that, for example, I equals 4 would give us this kind of reaction. And we need a fork to the right of philosopher 4 and the fork to the left of philosopher 4. So how do we achieve that? Well, we just define names for the fork to the left of philosopher I, for the fork to the right of philosopher I, and for the hungry philosopher I. And just as before, on the right-hand side of a case expression, it's fine to use the substitution. Now this syntax, again, this is a little inconvenient. You can just do this with no real difference. These are all non-blocking molecules, so the order in which we emit them doesn't really matter. But there's some syntax problems with the plus. Oh no, there isn't. This is what I should have done. Okay, so now this syntax is valid and this will work, but this is maybe not very readable. So I'm still in favor of doing this, so you can more easily understand what is the reaction that you're creating depending on the parameter I. So that's the reaction, which would be exactly like we had before, except now we have fully parameterized this reaction by the index I. So now we have created an array of n reactions for thinking, an array of n reactions for eating. Let's create a reaction site. It's very easy. Just do a site on the full array of reactions. You just need to adapt to the syntax of this variable argument function. And we're done. So we have created a reaction site. It remains to emit the initial molecules. How did we do that here? We just emitted all the thinking molecules and all the forks. So let's do that. We emit all the thinking molecules and all the forks. We're done. So the function run philosophers can be called now with a parameter. Actually, I just realized there's a mistake because this needs to be emitted rather than just the molecule emitter evaluated. So this syntax is actually harder to understand and to remember. So you see this change that I made is actually not great. Let's run the test. It should print a different number of philosophers thinking or eating. And we have now 10 philosophers that should take turns. Okay, so that's what I expected. For instance here, 7 is eating, 9 is eating, and 1 is eating. So they're all eating, but they're not next to each other. 7, 9, 0 is not eating, and 8 is not eating. So that's the kind of behavior we expected. So this was the first example. Let me now switch to the second example, where I implement the game of life in different ways. The goal of this implementation is certainly only a tutorial. So I want to explore how the chemical machine can express different patterns of concurrency. Certainly, this is not going to be a very high performance implementation, because the game of life is not easy to parallelize very efficiently. You have to spend a lot more effort than I'm going to spend. So the game of life consists of a square board, or a rectangular board more generally. Each cell in the board has a state, which can be then 0 or 1, which can be empty or non-empty. And there's a rule that the present state of the current cell and its 8 neighbors determines the next state of the current cell by this formula. And you add together all the values for the neighbors, and if there are exactly 2 neighbors that are not empty, then the state 0, which was your center of the central cell, the state 0 remains unchanged. If the sum is 3, the state 0 becomes 1, whatever it was before. Otherwise, the state 0 becomes 0. So the cell has the next state computed by this function. So the cell that previously had state 0, depending on the 8 states of its 8 neighbors on the rectangular board. So that's the standard game of life. And the only interesting part here is to parallelize this. So how do we parallelize this using a chemical machine? So let's reason about it using molecules. Clearly, the state of cells needs to be on a molecule somehow. So and also the state of neighbors, neighbor cells needs to be on some molecules. So let's say the molecule C0 will carry the state of the board at the cell with coordinates x, y. And then we have additional molecules, C1 to C8, that will carry the neighbor data for this cell. And let's put x, y as values also on the molecule, and also the time t. So at each time we will have some x, y, and these 8 molecules. So C0 is in the center, and then 1, 2, 3, 4, 5, 6, 7, 8 are around it. So this is how we could imagine this to be. And the molecule therefore carries a quadrupole, a tuple with 4 parts, x, y, t coordinates, and its state. So this is how we can model the board. Now, clearly, this cannot work, because we cannot use the same x and y in a case expression. So x, y, t are pattern variables in the case expression. Our idea was that the molecules representing information for this cell will all react together. And so C0 of, say, 5, 5 would only react with C2 also of 5, 5, and C1 of 5, 5, and so on. But this cannot be represented by simply repeating the pattern variables. So that's invalid syntax. So, well, that's what we have to write. We need to introduce different pattern variables in each term, and then add a guard condition that will assert that all of these are equal. So that works. And now the right-hand side of the reaction needs to be understood. What should we do? Well, we should obviously emit new molecules that represent the new states. So first of all, let's compute the new state. So we use that function we defined above. And then we can emit C0 with the new state and the new time. But if we just emit C0, then the next step will not work, because the molecule C0 wants to react with all its 8 neighbor data, which we did not emit. So we need to actually emit all 9 output molecules with the different coordinates. So this is how we emit this data. Let's look at the code actually. So this is the Scala code. I use the cell as a case class actually, instead of just a tuple. So this case class is defined like this. It has additionally a label. So the label represents which neighbor we're dealing with. And so this actually uses the same molecule for all eight neighbors. And we get a new state, and then we emit actually using for each, rather than writing code by hand like this. But this is equivalent. So the final touch is that we need to wrap around somehow. We need to deal with the edges of the board. So let's, for simplicity, just wrap around using the modulo computations. So that result would look like this. And that's what you see in the Scala code. There's this modulo computations. So that's actually the second test case rather than the first one, where we have 8 molecules, and this is the reaction that we just described, using the case class as the value of the molecules. And you see we can just pattern match directly, pattern match on the value of the molecule as a case class, introducing pattern variables. So this illustrates that actually the reactions are defined using just a normal Scala case expression with all features that you want in it, including arbitrary guard conditions and arbitrary pattern matching. So this works. To test it, we make it some initial board with some glider configuration, and we run the test. So there's this G function that is defined for convenience to return the board when the board is finally computed. And what we do is we just count a certain number of time steps, and after that we emit the molecule F, which means F with 0, which is what we react with here. So once we get a 0, we finish. And in this way, we count a fixed number of time steps. So I'm skipping over other things that are going on in this code. They're thread pool configurations. They're not essential for what I'm explaining. Now, let's actually look at the first test. In the first test, we had a reaction with one molecule only. So this one molecule had an even larger state, which had a coordinate x, coordinate y, coordinate t, state, and the label. And then this is actually equivalent, because you can have different molecules, or you can have the same molecule that carries some label value on it. So in principle it's equivalent, and the code is a little simpler perhaps, because rather than having to write out this entire thing, C1, C2, C, and so on, we just have a loop. So that's kind of more understandable. However, the performance of these implementations is very bad. It's actually very, very bad. And the reason is that there is this very complicated guard condition. So in order to start the simulation, we need to emit 8 molecules per cell on the initial board, and also the molecule itself. So per cell, we emit 9 molecules. We need to emit 8 neighbors and the center. So we have a very large number of molecules that could potentially react to each other, and the chemical machine needs to go through all the possible combinations of these molecules, trying to find which ones satisfy the guard condition. And we have a very large number of variables that need to be fitting the guard condition. So it's very slow to enumerate all the various combinations of the molecules that could potentially react according to this reaction, and then examine the value of all of these variables and compare all these things. Now the chemical machine tries to optimize such computations, but there's not much we can do really. We have a 5x5 board, and so there's 25 molecules C0, there are 25 molecules C1, and so on. And we need to go through all 25 of them, potentially, to figure out which one would be the first here to react, and then another 25 to go through to figure out the second one, and so on. So this is a very large number of possibilities. And the result is that reactions are scheduled extremely slowly. Each reaction is fast. This is not a lot of computation here, but the scheduling is extremely slow. And the first test is even slower because it has a single molecule C, which is emitted 9 times per cell. So it's 9 times 25, which is 225 molecules. And so it needs to go through 225 here, times 225 here, times 225 here, and so on. And each time finding what conditions might be satisfied. So it is optimized, so it does not actually first go through all possible combinations and then apply the guard condition. It actually goes in much more optimized way, one by one. First it takes the first one, then it selects the second one that fits, then it selects the third one that fits the first two, and so on. That's what it does. But nevertheless, it's very slow. So how do we make it faster? Let's see. Now the reason for bad performance is not just the complicated guard condition. It's the fact that this condition mixes together properties of different molecules that are inputs in the reaction. So this is the reaction, and the guard condition is a cross-molecule guard. So it's a condition that mixes together all the different values from different molecules. So this first molecule is coupled with every other molecule through a guard condition. So you cannot separately select the first molecule and then separately select the second molecule. The choice of the second molecule depends on the choice of the first. The choice of the third also depends on the previous choice, and so on. So this is the source of the slowness in the scheduling. And this is what I call the cross-molecule guard. And these are usually much slower because many combinations of molecule values have to be examined. And that needs to be avoided if you can avoid it, if you see such bad performance. And let's think about how we can avoid it. So the main idea is that we needed to select molecules that should react together. And we just did it by hand. We put labels on molecules and selected by values of these labels. Instead of doing this, we can define a separate reaction for each group of molecules that react together. And then they will automatically be selected for each other. There won't be any search through all the combinations. Each scheduling will be very fast if we do this. So in order to do this, we need to use a different chemical sort of molecule for each set of coordinates. So that's an important concept in the chemical machine, the chemical sort of molecule, or a chemical designation of a molecule. Each molecule emitter has a different chemical designation. It's not the name, it's not a string. It's in Java language, it's the object identity of the molecule emitter. So every time we create a new molecule emitter, we automatically make a new chemically different molecule that can react differently. So let's create a large array that will have all those molecule emitters. That's easy to do. We can just create such an array by using this kind of emitter class constructor, where we just, for convenience, put an interesting label name on each molecule emitter. So as a result, we'll have a large matrix of emitters. Now we need to create reactions between them. So, for instance, this would be a name of one of the molecules. So we need to correctly define reactions between them now. So we will have a reaction matrix as well, of course. So we just do what we did in the dynamic philosophers case. We need to define names that we will use to define the reaction, because we cannot directly say emitter matrix blah 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 of state 0 on the left hand side of a case expression. So now we just say these are the molecules that should react, these are the parts of the emitter matrix that should react, and this is their reaction, and this is the new molecules that are going to be emitted. So that's basically what we did before, except now everything is parameterized and we have an array of these reactions. So we return a go of something inside this array tabulate call. And so the result is going to be an array of reactions. Now you see the explicit type here. Reaction is the type of the value that you create using the go macro. Now, after creating all the reactions, we just put them into reaction site. We need to flatten this twice, because the reaction matrix is an array of arrays. So flatten it twice, we're done. This works. This is actually example 4. Test 3, let's see what test 3 is. I have a 9-molecule implementation where I have a smaller emitter matrix, basically. I have an array of array, and I don't have t, so that the time t is not present here. So that's already a big improvement. The time is now on still here as a state. And I still have a guard condition on the time. But this is already much faster. And test 4, okay, so this is, I can already run 10 by 10 board, whereas before I couldn't. I had a 5 by 5 barely. Now, there are different versions of this, differing by how I organize the emitter matrix, but they're not significantly different. So I'm interested in looking at test 4, because these are the per cell reactions. That is, I have a different molecule emitter for each cell, for each time, and for each neighbor. So that's going to be the case for implementations 4, 5, and 6, whereas in the previous implementations I always had some extra information on the molecule that I had to use a guard to select something. Now I have no guard condition anymore. So these implementations are much faster because I have no guard condition anymore. And that's the code. Very simple change, and same thing that I had before. And now I can run 10 by 10 and it works. So actually it's much faster, but when I ran the example, I found that the concurrency is actually not happening. The parallelism, strictly speaking, is not happening. The reason is that there's a single reaction site that runs all reactions, and it schedules one reaction at a time. And so the reactions are very simple, and we don't have any parallelism. We schedule one reaction, then it runs very quickly. Schedule another one, it runs very quickly. So now we just noticed that actually we could define separate reaction site for each reaction, because each reaction takes its own different set of inputs, which are these, C0 to C8, and they're different for each reaction. So for each XYT in the reaction matrix, there are different inputs. So no two reactions contend on the same input. And that's why we can define each reaction in its own reaction site. And that's how we would do it. It's just now there will be one reaction site per cell, actually per time unit, per time step, and per cell on the board. And that's the test 6. It's the fastest. We spend more time upfront creating these reaction sites per cell, but it's much faster to run because it's fully parallel in both space and time. Each cell at each spatial coordinate and at each time can be scheduled in parallel with all other such cells. So this is this test. Now, the difference between implementations 4, 5, and 6 is only in how the reaction site is created. Here, there's one reaction site for all reactions. Here, there's one reaction site per time slice. And here, there's one reaction site per cell. So the code is very cleanly separated now. We create reaction sites separately from reactions and from molecules, and we're very flexible about what we can define and when. We can first declaratively define the logic. We define reactions separately. these definitions don't actually start anything, they're just values that we can store in a data structure. Finally, we activate them in the reaction site, and then still nothing will run because we need still to emit the initial molecules before anything will run, but it's ready now and activated. So in conclusion, we have learned two things in this tutorial. First, a chemical machine, as implemented by the Chymyst library, allows you to define molecules and reactions using the full power of a Scala language. You can use functions, you can parameterize molecules and reactions in arbitrary ways. You can use cross-molecule guards if you need to. You can use arbitrary guard conditions, arbitrary pattern matching, and organize your reactions in arbitrary ways in reaction sites. So you can first define these reactions as values, molecule emitters as values. You can define arrays of them if that's what you need. And then you can put all of them into a reaction site, or you can make many reaction sites also using the full power of the Scala language, because reaction site creation is just a function call. The second thing we learned is that the chemical machine will run very slowly if there are lots of reactions in one reaction site, because the chemical machine will not be able to schedule many reactions at once. It will schedule one reaction at a time. The scheduling may be fast, but it will still schedule just one reaction at a time. So if you need to start 1,000 reactions very quickly, that's not the way to go. You need to have many independent reaction sites that will schedule this in parallel. Now, all reaction sites that you create separately are going to be concurrent with each other. They're going to schedule reactions separately and concurrently with each other in parallel. If you can avoid cross-molecule guard conditions, then you would avoid the situation when scheduling even a single reaction can take a very long time, which is obviously a very bad situation, which we have seen in the first tests of the game of life, where everything was done in a single reaction with a single or a very small number of molecules that had very complicated data on them, and the guard conditions selected which molecules should react to each other according to a complicated expression using all this data. So that is a very bad idea for performance in the chemical machine. It is intentionally shown here in this tutorial as an example of what not to do. Avoiding repeated input molecules is speeding up things. Avoiding cross-molecule guards is speeding up things. And avoiding one reaction site with a large number of reactions is also speeding up things. So with this, I conclude the tutorial on dynamic reactions in the chemical machine.